Okay, so in this video, we're going to look at a Z-score summary because you should have watched a previous video on the 68, 95, 99.7% rule. And then we're going to do some work examples. So just before you do that, I'd suggest either take something like this one here or this one here and put that in your summary book because it makes the link between the percentages, the standard deviations, and the Z-scores. And this one does the same thing. So the standard deviations are here, the Z-scores are here. Okay, so you can see that link and you've got your percentages as well. And just as a quick overview, remember that's 68% of your data, that's 95% of your data, and the third one is 99.7% of your data. Okay, but also remembering that when you, sorry, I just want to erase that. Just remember that when questions can arise where it can be asking for basically that 16% part or that 2.5% or that 0.15 here or that 0.15 down here. Okay, and you have to be aware of what that means. All right, so it can mean that if your standard deviation is 60, your mean is 60, your standard deviation say 5, and ask for what percentage of people have got a score below 35, you'd say 0.15%. Okay, that's how you use it. If you're not sure about that, check with me anyway. All right, so that's the summary part there. Worked example. All right, the risk circumferences of a large group of people were recorded and the results are shown here in this histogram, and that looks approximately symmetrical. So the mean of the said data is 17.7. So that's sort of, if you're thinking about that pattern, that's going to be 17.7. So x bar is equal to 17.7. Now, the standard deviation is 0.9. So when we say 68%, we're talking about one standard deviation. So A is going to be, remember, x bar minus plus or minus SD. So 68% is one standard deviation both sides. So it's going to be 17.7 plus 0.9 equals, and it's also going to be 17.7 minus 0.9 equals. Okay, so I went ahead and calculated that value, so I put that in there. So it'd give you 18.6 and 16.8. So that's where 68% of your data lies. So that corresponds to that. So let's do 95%. So 95%, so what we're saying here, that's x bar plus minus 1 standard deviation. This is x bar plus or minus 2 times standard deviation, and x bar plus or minus 3 times standard deviation. Okay, so when we look at these ones, I calculate, so that's where the 2 comes from here, and I get 19.5. I subtract that, I get 15.9, and when I do 3, so 3 times 0.9 is 2.7, and that's where I get these values here. So that's how you do that for that sort of question here. So let's look at this worked example. We've got a distribution of masses of a large number of packets of this breakfast cereal is known to be bell-shaped. So bell-shaped, we say we can use this rule. That's the key word to tell you in this particular question. Okay, so it's got a mean of 250 grams. So important to highlight as I've done there. And so that's my x bar equals 250 grams, and my standard deviation equals 5 grams. Okay, find the percentage of fiber-filled packets with a mass which is, and we're going to use those examples there. So I'm going to pause this for a moment, and I'm going to get the graphic so we can use. Okay, so here's the graphic we can use in a moment. So when we say less than 260, okay, what we're saying is, so 260 is how far away from 250? It's 10 grams. That's 2 times the SD. That means we're looking at this one here, and we're looking from this point, and we're going that direction. Okay, so it's most of. So so we're going to say that's going to be 95%. Okay, did I get that number right? Because clearly I can't read. It's actually 97.5. Okay. All right, because if you look, that's worth 2.5%, and the rest is being covered there. If I go less, so if we're going to do it like this, let's actually, oops, I'm not meant to erase. Let's actually put a bit of some stuff here. So we're saying that's 250, and it goes in five. So that's going to be 255, 260, 265. 245, 240, 245. Have it written on there so you can actually really see what's going on. So now when I say less than 245, I mean that. Okay, so that's 13.5 plus 2 points, so that's going to be 15%, 16%. Sorry, not doing good with my addition today. 16%. Okay. So that means our question answer here is going to be 16%. More than 240? Well, 240, that should have been 235, sorry. More than 240, so I'm looking at that lot, okay? Again, because we're looking for, that's going to be another 97.5%. Because remember, that there is worth 2.5%. And that means the rest of it's going where we want it to go. Okay, between 240 and 245, so 240 here, okay, and 255, so it's going to be 68 plus 13.75, and that will give you 81.5%. So that's how you can use this information to work out what's going on. So here's another worked example. We're going to use this thing again as well. So let's erase some of that. Okay. All right. So this question says number of matches not always the matches in box not always the same. Got a sample. We found it's got a normal bell-shaped distribution, so we can use this. Remember, that's our key. It's got a mean of 50, so that means I put 50 here. Standard deviation of 2 either side, so that means that's 48. That's 52, that would be 54, that would be 56, 46, 44. Now, I don't need that for this question, but I'm just showing you what, just to make it very clear. So in a sample of 200 boxes, how many would you expect to have more than 48 matches? Now, here's where you've got to get the percentage and then use that percentage value to work out the number of boxes. So what do? I look at where 48 is. 48 is here, so that means it's all of that. And if you can calculate that, that would mean that I'm going to get more than 48. Let's write more than 48 matches is going to be, so that's equal to 84%. So that's 68 plus these 13.5s plus 2.35 plus the 0.15. Okay. Or another way to do it is to say that's 50% and that's 34, so get 84%. Okay, now I take that 84 and go, well, that's 84% of 200, 84%, so number of boxes equals 84% of 200. That means 84 divided by 100 times 200 would give me 168 boxes. Okay. Okay, here's just another couple of questions on this. I've got another 3 worked examples. I'm not going to do all of these ones, okay, because they'll take too long. I'm just going to do like 1 or 2 of them. So mean of 9 days. So this is where it's in a workplace. approximately bell-shaped. That's our key point. We can use this particular rule. Okay, so mean is 9, standard deviation 2, so that's going to be 11, that's going to be 7, that's going to be 13, that's going to be 15. If you want to write it, you don't have to write up the top, you could write it like here, 9, 11, 13, 15. Write it wherever it suits you best. So 7, 5, and 3. Okay, so more than 15 days, percentage, more than 15 days, that's there. So it's more than 3 standard deviations, so that's going to be 0.15%. Okay, fewer than 5 days, so I look at where 5 is, it's this point here. So it's going to be 2.35 plus 0.15, so that's going to be 2.5%. Maybe I can do it more quickly. More than 7 days, so 7 days is here. We know that that's 50 and that's 34, so I'm going to have 84%. Between 3 and 11, so I'm going from this point here to, where's 11? 11 is here. So it's going to be 68 plus 13.5 plus 2.35. So 68 plus 13.5 plus 2.35. That would give you an answer of 83.85%. Okay, between 7, so 7's here, and 13, it would be, I think it's 81.5, because I'm going 68, because I know what that is there, plus 13.5. Okay, so that's how you'd calculate, work out a question like that one there. All right, so I'm going to copy this down so we've got something to refer to here. All right, so in an IQ test, the mean IQ is 100 and the standard deviation is 15. What's the Z-score? So his test results, his test results are 130. Okay, so that's where we use a formula, Z equals X minus mu over, okay, we've seen that written as, let's keep that there, you can write it X minus X bar over S, okay, X over X bar minus S. The X, the mu and the X and the X bar and S are just terms in terms of, this is talking about population, this is talking about a sample. So most of the time, we're going to be using this one here. Means the same, for our purposes, it means the same thing in terms of how we use the calculation. So that's going to equal, okay, his score was 130, so I put 130 in there. Okay, his the mean for this was 100, so I minus 100, and the standard deviation was 15, and that gives us a score of 2. So if you looked at say something like this, 2, you know, he's up in this category here in terms of where he's relative to everybody else. So he's got a IQ score that's 97.5% higher than the rest of the population. Okay, so his last worked example. So Janine scored 82 in her physics and 78 in her chemistry. In physics, she got physics, the mean was 62 with a standard deviation of 10. Chemistry 66 and 5. So let's look at the results. So let's say chem. Actually, write it physics as it's got there. Chem's better. Chemistry. Okay. So Z scored here. So let's highlight physics 82, mean 62, and standard deviation was 10, 78, 66, and 5. So let's have a look. So Z, the score was 82 minus the mean was 62. Divide that by 10. Okay. Chemistry, it was 78 minus 66 divided by 5. And that's going to give you values of 2, and that's going to give you a value of 2.4. Now remember, if you looked at something like this, 2 would be here. So basically, relative, say, everybody else in the class or the cohort, he's better than, she's better than 97.5, but 2.4 is somewhere up here. So they're going to be doing better than the other person. So basically, so that's for A. For B, you're doing better in chemistry. Chem result is better because of high Z-score. Better because of higher Z-score. Oops, that's a C. I can't even spell properly. Okay. So there's some worked examples for you. Thank you.